All right, ladies and gentlemen, here we got the notes for section 2.2, limits involving infinity. So we've got two objectives, find and verify in behavior models, and then calculate limits as you approach infinity. So finite limits as x approaches infinity are either positive or negative. The one thing to remember is that the symbol for infinity isn't a number, it's a concept, because you can't count to infinity. There's always a number after the one you've just said, so you'll never actually reach it. So what we have here is horizontal asymptotes. So the line y equals b is referred to as a horizontal asymptote with the graph of the function if either the limit as you approach infinity or negative infinity is equal to that value. So what that means is the graph will level off at some horizontal line, essentially, as you go off either the right for positive infinity or left for negative infinity. So example 1 here says use graphs or tables to find the limit as you go to infinity, negative infinity, and identify all horizontal asymptotes of f equals x over square root of blah, 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 blah. So I'm just going to draw the graph here. Whoops, got to get everything cleared out my calculator. So we've got x over the quantity, the square root of x squared plus 1, double close, draw. Okay, so zoom out. Okay, so here's my graph. You can see it there, looks like that. So if you notice, as you go off the right to positive infinity and off to the left to negative infinity, the graph flattens. And if you use the trace command, you can see that the y values get closer and closer to 1, but they never actually will reach 1. So for both of these, going off the right, it was positive 1, it's up here. Off the left, negative infinity, it is negative 1. So the horizontal asymptotes are y equals 1 and y equals negative 1. So squeeze theorem again. So just find the limit as you go to blah, blah, blah. So I'm just going to use the graph. So the sine of x over x. Oops, need to make sure I'm in radian. Otherwise, a trig function will not graph correctly. So view window, initial, draw. So it looks like this. So if you notice, the graph is flattening out. When I zoom out, you'll see even more. So in either case, the asymptote is 0 for both the left and the right. Oh, this one just wants the positive. So this limit as x approaches infinity of sine x over x is equal to 0. As you go off the right side of the graph, the y values get closer and closer to 0. All right, so a bunch of properties as you approach infinity. Sum rule, so these are actually all the same rules as we had before. We're approaching some number, but the rules also work for infinity. So if f has the limit of L and g has the limit m, if you add f and g, you add the limits. If you subtract them, you subtract limits. If you multiply them, you multiply the limits. If you multiply f of x by some constant multiple, so you double the equation for f of x, you can just double the limit. If you do a division problem, you divide the limits, assuming that g does not have a limit of 0, because otherwise you're dividing by 0 and it's not allowed. And lastly, the power rule. If you raise your function to a power, it's just the limit to that power. So if I know f of x has a limit of 4, and I raise it to the 1/2 power, then it's just the square root of 4, which is 2. Okay, so example 3 here, find the limit as you approach infinity of 5x plus sine x all over x. For infinite limits, a lot of times it's easiest just to use the graph, to be honest. So let's look at the graph. So 5x plus sine x over x. Draw the graph. Looks like that. So if you notice, it's way up there. So we'll trace it. So you can see the y values bouncing back and forth. So it looks like it's leveling off at about 5. So this is just equal to 5. Okay, so our next topic down here is infinite limits. So this is a limit as x approaches some number. So what we're going to have is we're going to approach the value and get a vertical asymptotes. So the graph will go, the y value will go to infinity. So that looks something like, if you remember graphs that have like this kind of shape, so like a spike on it. So this line right here is a vertical asymptote. The line will approach that vertical line but never reach it. These are infinite limits. The graph goes to positive infinity or negative infinity. Can't get my pages turned. There we go. Okay, so example 4 here, find the vertical asymptotes of f of x equals 1 over x squared to describe the behavior to the left and right of each vertical asymptote. So we'll sketch the graph real fast. So 1 over x squared, draw, looks like this. So it does that and that. So when it says from the to the left and to the right of each asymptote, so what that's saying is, so the asymptote here is at 0. So the limit as x approaches 0 from the left, and f of x, and the limit as x approaches 0 from the right. So as I approach 0 from the left, the graph climbs, so this is positive infinity. As I approach 0 from the right, the graph climbs, so also positive infinity. The graph of 1 over x will have one at positive infinity and one at negative infinity, but since this is x squared, the y values will always be positive because you're squaring something. Okay, end behavior models. So for large values of x, we can sometimes model the behavior in a complicated function by a simpler one that acts in the same way. So this says let f of x equals 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6, and g of x is 3x to the fourth. Show that while f and g are quite differently for small values of x, they're virtually identical for x large. Now this is absolute value, which means that either off the left or right, you're getting the same thing. So I'm going to graph these two functions. So we have 3x to the fourth, minus 2x, oh dear, typed that definitely wrong, 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6, so there's f, and then g is just 3x to the fourth. Draw. Okay, so should have got my other calculator for this. So if you look, how do I want to do this? We'll look at the initial window. So if you scroll up a little bit, you can see, so it says for small values of x, that means close to 0. So if you look at close to 0, this is 3x to the fourth, does this, and that is, so g of x, and this guy up here is f of x. So they are different, like this one, if you look at the graph, g of x goes all the way down to 0, f of x only goes down to about 4, so on and so forth. But if I keep zooming out, you'll notice that the graphs start to look nearly identical and you can't tell them apart. So you can see that they kind of start sitting on top of each other. Desmos can make this even more obvious, but that's what's happening. So as you zoom out, eventually they both just start to look like they start to overlap each other. So that's what that's talking about. So this is for large absolute values of x. What that means is that g, keep bopping the camera. What that means is that g is referred to as an end behavior model, because at the ends, as you go to positive or negative infinity, the graphs look identical. So a right end behavior model, if you divide the two functions, you get 1. If you go to positive infinity, same thing for negative infinity. So if one function provides both a left and a right end behavior model, it's simply called just the end behavior model. So you could have one equation for the right side, that's the right end behavior. One equation for the left side, that's the left end behavior. If they happen to be the same equation, then that's just called the end behavior model. You don't have to say left or right. Okay, so which brings us to example 6. It says find an end behavior model for these two functions. Now, the easiest way to find end behavior models is actually using a trick. What's happening is, the reason end behavior works is that as x gets very, very large, it's only the term that has the highest exponent that actually matters, because it essentially swamps all the values. If you think about it, if I start plugging in larger and larger x's, when x gets to be, say, 100, 100 to the fifth times 2 is a really, really large number. Adding 1 to it doesn't really change that number very much in the scale of things. It's like if you made $1 million in a year and someone gave you a penny, that doesn't really change your net worth that much. But when x is small, if you're only making, a couple dollars, getting an extra $1 or $2 here or there makes a big deal. So what end behavior says is that I can ignore any term that does not have the highest power. So like this, I could rewrite as just 2x to the fifth, the highest power in the numerator, over 3x squared, the highest power in the denominator, and just reduce that fraction. So 2, and then I'll have an x cubed left on top. These two x's cancel 2 of the 5 out, leaving 3 behind. So that's the end behavior model for that f of x function. I can do the same thing over here. I can worry about just the highest powers. So on the numerator, that's 2x cubed. In the denominator, that's 5x cubed. And then I can reduce this. So this will just be 2/5. Now, if you get a number, that means that the end behavior will be a flat line. The graph will flatten out. If you get an equation, the graph will still be curving, either growing or falling, depending on what it's going to be. Okay, so example 7 here says let f of x equal this, so that g of x is a right end behavior model, while h of x is a left end. So right end behavior means that if I take, how do I write this? I take f of x over g of x and take the limit as I approach positive infinity. And if this is equal to 1, it's true. Now I can do this, I'm going to do this conceptually, not necessarily mathematically. So if I plug infinity in here, remember that e to the negative x is 1 over e to the x, because the negative exponent drops you to the bottom. So what's going to happen is if I plug infinity in here, I get 1 divided by e to the infinite power. Well, e to the infinite power is a very, very large number. And if you have a fraction, if the bottom of the fraction gets very, very, very large, the whole fraction gets very, very, very small. So this fraction essentially becomes 0, leaving me x over x, which is 1. Which makes it an end behavior. So the limit came out to be 1. On the left-hand side, I take my f function, put it over this guy. Now remember, this is going to be x over 1 over e to the x, all over 1 over e to the x. So now x is going to negative infinity. So if x becomes negative infinity, that actually flips this, must be a plus sign there, back up to the top, because it has a negative exponent again, which turns it over. Now, e to the x, if I start plugging bigger and bigger numbers in, will grow faster than just x will. So e squared is bigger than 2, e cubed is bigger than 3, e to the 4th is bigger than 4, so on and so forth. So this term here, the x, doesn't actually matter, which leaves me just e to the x over e to the x, which is 1, an end behavior model. So this is just talking about the graph again. So find the limit as sine of 1 over x just by looking at the graph. So clear my old ones out here. Whoops. Sine of 1 over x. Draw. And we need to fix my window again because I zoomed way out. There we go. Okay. So we're looking for the positive limit as I go to positive infinity. So positive infinity is off the right-hand side, and if you look, this graph is dropping, 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 and eventually will reach 0. So the limit as x approaches either positive or negative infinity of, no, sorry, it's not f sine of 1 over x, it's just 1 over x. You make the graph of y equals f of x, as x approaches y, the graph of y equals. Oh, okay. Sorry. I'm doing this example. I did it right. I was reading the wrong part. So this goes to 0. What that's saying is that instead of finding an infinite limit, you could also find the limit as you go to 0. But if you do that, you take the reciprocal of the x term. The trick is 1 over infinity is the same thing as 0. So the reciprocal of infinity is 0, and vice versa. Reciprocal of 0. Now this doesn't get used a whole lot because it's easier, especially if you have a graphing calculator, just to graph the function. You don't have to worry about doing reciprocals, but mathematically that is how it works. Which brings us to the end of this section.